Here is my screen. And now let's go to our lecture. So, yesterday we discussed that with necessity we have a notion of strong random operator. Let me recall you what is it. So, strong random operator in a real separable Hilbert space H. This is a correspondence which maps elements of H, elements of H into random elements in the same space. Random element. And such that it is linear. Is linear. And A is continuous in probability. Yesterday, we have seen several examples of such objects where one can get the following feeling. First of all, A is not always a family of bounded operators indexed by the points of probability space. We discussed several examples which shows us that in general there are no the mapping from omega to LH such that we have this property. Yeah. So here omega fp is a probability space. So there are no such presentation in general. But sometimes we have it, and sometimes it is useful to understand how it works. Last, what we did yesterday was a discussion about self-adjoint random operators. So let me recall you what we discussed, and then we will have some statement about the structure of self-adjoint random operators. So let me recall you that deterministic non-random operator A is called self-adjoint if for all x and y which belong to H, we have the following relation. Ax y is equal to x ay. I recall that we consider real, not complex, separable Hilbert space. Also, I am supposing that A is bounded operator. There exists a rich, interesting, and very powerful theory of unbounded self-adjoint operators, but for our purposes, it's enough to consider bounded linear operators. We discussed that in case when H is equal to RD, so if H is a finite dimensional Euclid space, then A is a symmetric matrix. Matrix, and A has some orthonormal basis E1, ED. This is orthonormal normal basis, and this basis consists of eigenvectors of operator A. So AEK is equal to lambda k on to EK. So we have a complete set of eigenvectors and eigenvalues. And last, what we mentioned yesterday was the simple consideration which shows that there are examples of bounded self-adjoint operators in infinitely dimensional space H such that there are no eigenvectors. There are no eigenvectors. So to understand the structure, we need something else. And to do this, we will discuss the spectral theorem. For self-adjoint operator. Namely, let me consider the following generalization of the notion of eigenvectors. I will discuss the projections. So let us recall a definition. Q is orthogonal projection in H onto subspace M if for all X which belong to H. Q of X is equal to xm, where we just use xm from unique representation. X is equal xm plus x orthogonal, where xm belongs to m and x orthogonal is orthogonal to m. So it is very well known from Fourier's orthogonal projections. For example, if we have H equal to R3 and M is a subspace of vectors whose third coordinate is equal to 0, so M is like alpha 1, alpha 2, 0, where alpha 1, alpha 2 belong to R. Then orthogonal projection on M, Q of alpha 1, alpha 2, excuse me, alpha alpha 2, alpha 3 is equal to alpha 1, alpha 2, 0. So, when we have, for example, a finite dimensional Euclid space, then one can construct projections, every projection as follows. In case dimension H is less than infinity, any projection has a form Q x is equal to sum from J equal 1 to M x J J J, where J is orthonormal system. Is orthonormal system. Not basis. It can consist from one vector, for example, despite the dimension of H can be equal 1 million. But still, any finite dimensional projection can be described as I proposed. Why I'm speaking about this structure of finite dimensional projection? Because let me recall that if we have a self-adjoint matrix adjoint in RD, in finite dimensional case, yes, then we have the following statement. A is corresponding to the orthonormal basis EK k equal 1 to d, and number and set of eigenvalues lambda k equal 1 to d. And now we can organize a special projections related to these eigenvectors. Namely, let us use the same formula. Let us take a projection which has this form. So it is equal to sum from j equal 1 to m, x e j e j. Why I'm considering these projections? Because they have a very interesting property. Let me emphasize that now these projections are commuting with A. So we have QA equal AQ. Yes? Please check this. So now we have a family of projections which commute with our self-adjoint operator. In some sense, one can say that these projections are also eigenprojections for our self-adjoint operator. And it occurs that in infinitely dimensional space, when we have no eigenvalues and eigenvectors, we still have these eigenprojections. Such projections, let me, for a moment, this is not a mathematical term. Eigenprojections still exist in infinitely dimensional case when dimension h is equal to infinity. Let us look, for example, and you remember example from the yesterday lecture. It was the following very simple operator. We consider the space L201 as a space H, equal to H. And our operator was just a multiplication on the free argument. So H of t was equal to t multiply on H of t. Of course, it is self-adjoint operator. And now I think that at least some of you tried to solve the exercise from last lecture, that this operator has no eigenvectors, non-trivial eigenvectors. So now let us check that it still has eigenprojections. Namely, define for any t0 which belongs to half interval 0, 1, defines the projection q t0, which will act on the function h as follows. This is simply a multiplication on the indicator function of the interval 0 t0 from t ht. So we just do the following. Here is our function h on the interval 0, 1. This was a function h. And we have here t0. Then we just make this one. We cancel this, yeah? And a new function is equal to the following. It coincides with 0 after T0, and here it is equal to H niche. Yeah. Okay. It is trivial to understand now that Q T0 A is equal to A Q T0. And it occurs that it is common situation that if we have a self-adjoint operator is a bounded self-adjoint operator in H then there exists unique family of eigen projections I will index this family by the set delta, where delta is a Borel subset of R. Let me BR R Borel subset. R. Such that here we have the interesting property. The first one, as we mentioned, Q delta A is A Q delta. So we can say that Q delta is a projection on the eigensubspace of A. The second one is that for delta 1 and delta 2 such that they have empty intersection, we have the following Q delta 1 multiply Q delta 2 is equal to Q delta 2 multiplied Q delta 1. It is not necessary to point the second equality, but for simplicity, and is equal to 0. It means that for non-intersecting subsets of R, we have projections on the orthogonal subspaces. The third one is that if we have delta 1 delta n such that delta k intersect delta j is equal to empty when k is not equal to j, then we have the following Q from the union from k equal 1 to n delta k is equal to sum from k equal 1 to n q delta k. In some sense, we see that we have a measure with the values in projections. Moreover, it occurs to be true that if we have if we fix or fixed h, which belongs to H capital, one can consider QH, Q delta H, and it will be a measure is a Hilbert valued, is a H valued measure with the orthogonal values on disjoint set. And one can easily define the integral with respect to that measure. And finally, we have the following relation. A of h is equal to integral from minus to plus infinity lambda d, I say, okay, let us not to invent new notations. Q d lambda of h. That's all. So we have the following integral representation of our self-adjoint operator. From this point of view, one can see that spectral theorem is just a generalization of a usual decomposition of symmetric matrix onto one-dimensional subspaces generated by its eigenvectors. In general, we have no eigenvectors, but still have these eigenprojections, and still we have such a good representation. In case when we have A is matrix in RD, this representation looks like AH is equal to some, instead of integral, we have some lambda k 1 to d lambda k x, excuse me, not x, h ek ek. So I can say that Q from delta is the sum from k equal 1 to n delta lambda k, where it is a Dirac delta function, multiply on the ek. This is one-dimensional projection onto space generated by ek. So in this case, and here is delta. In this case, we have such a simple representation of the spectral measure. Sometimes Q is called by spectral measure of self-adjoint operator A. Why I'm talking about this? things about the structure of self-adjoint operator, because it can be proved, it was proved by Skorokhod, that if A theorem, if A is a random bounded self-adjoint operator, excuse me, operator, then projections Q delta. Now let me emphasize they're depending on omega, because H depend on omega. Can be chosen in measurable way. Namely, all all H and delta from Borel subsets of R Q delta H is a random element, in H. So sometimes one can think about the random operators in the following way. Okay, we have some good structure for deterministic object. Then, if it is random, we also will have some good structure. Yes, sometimes it is true, but now we will go to the opposite situation. We will consider non-bounded Gaussian random operators. Before to go to this non-bounded Gaussian random operators, let me say that this theorem can be proved using the integral representation from integral representation for eigenprojections. There exist the integrals from resolvent of operator, which give us a value of the projection of the fixed set. But since it is not a subject of our lectures, we don't consider the proof of this theorem. Just we have it and we will use this theorem in the future, which emphasize for us that sometimes good deterministic structure can be kept in a stochastic situation. Just saying, okay, all elements of this structure are random now. And that's all. Now let us go to Gaussian on random operators. I will say here, let us use the following definition. That a strong random operator random operator A is Gaussian, if for all H, AH is Gaussian random element, a random element in H. Before we start to study all the Gaussian random operators in all generality, let us look for simplest example of Gaussian random function. So if AH is a Gaussian random variable, we will say that A is a Gaussian function. It is completely this definition completely coincides with the usual notion from functional analysis, where we call operator if it exists in some vector space, and we call object to be functional if it exists into the real numbers or complex numbers, depending on the case which we consider. So what we can say about strong Gaussian function? I insist that they still can be unbounded. And maybe example from the previous lecture also will work there. Let us consider it again. So let us consider the following example. Suppose that psi n are, be independent standard Gaussian variables. Let also En as before be orthogonal basis in H. Also normal basis in H. Let us define A H. I will denote it in brackets because it is more common for notation of the linear functional. As follows: it is a sum from n equal 1 to infinity, psi n. Here we have h n. Now the question is whether the series converge. And let me emphasize that the series consists of independent centered summands such that now the expectation, the sum of expectations of the squares h n square is less than infinity. So by the theorem about two series, the AH is properly defined. The series converge almost surely. One can say that this series n to infinity psi n h e n converge almost sure. Those of you who was carefully listening the previous lecture now get a feeling that here we have a problem because this almost surely depend on this h, and it is true. It is true. So one can check that a is not a randomly chosen continuous functional on our space H. Why? Why it is true? In opposite case, due to representation theorem, A must be a random element in H, namely the series sum from n equal 1 to infinity psi n square must converge. But we already know that this is not true. But the sum from n equal 1 to infinity psi n square is equal to plus infinity almost surely. We discussed this more precisely last lecture, where we even proved that the sequence of psi n is unbounded with probability 1. So we have an interesting situation. We have no random element in H, but we have its scalar products. Yeah, its scalar products with other elements of H. It looks like we have a situation from the well-known book from our childhood, Alice in Wonderland, where we have Cheshire's cat. We have no cat itself, but we have its smile. The same happens here. We have just a scalar product. We have no element. We have scalar product with it from other elements of the space. So, from this example, one can ask how we can discuss this random Gaussian functionals. And it occurs that we can discuss it very easily, namely, we can proceed with the characterization of Gaussian random functionals as follows. Let A be a Gaussian strong random functional in H. And I suppose that it is centered. It means that for every H will belong to H capital, the expectation of AH is equal to 0. A of H. Yeah. Then what one can define? Consider the following bilinear form. Consider for all x and y, which belongs to our space H, the following expression as x, y is equal to expectation of a of x, here is a of y. I insist that this bilinear form is continuous with respect to both x and y and is linear, so one can discuss about operator S related to this bilinear form. To check it, we have only to check the following. S is continuous. How to check it? Let us mention that for all for all xn tending to x, when n tends to infinity, axn, 3xn tends to ax in probability when n tends to infinity. But let me tell you that now we have a centered Gaussian random variables. Axn, this one also, is centered Gaussian variable. Centered Gaussian. So then, one can easily check. For example, you can use characteristic functions method that they converge in square mean. From this one can they are not only Gaussian but jointly Gaussian. Gaussian jointly. So one can check that now A x n converge in L2 to AX when n tends to infinity. Due to this, operator x, excuse me, due to this, A considered as an operator from H to the space of all random variables which are square integrable has closed graph. Due to this relation, yeah, it's continuous, yeah, it is continuous. It is linear, and continuous, Consequently, there exists some constant c greater than 0, such that expectation of AH square is less or equal than c on the norm h square. Now it is trivial. Now our SXY, which is equal to absolute value of expectation of h of x, h of y, is less or equal than c c multiply norm x norm y. Then c is a continuous linear operator. A linear operator. Okay. Consider examples. In case AH is, as we discussed, it is a sum from n equal 1 to infinity psi n h e n as before. It is easily seen as is equal to identity operator. So one can see that our strong Gaussian functional now is related to identity operator. In this case, A often is called white noise. Call it a Gaussian white noise or simply white noise H. White noise or simply white noise. Excuse me. Excuse me. White noise. White noise in H. H. S is called by covariance operator. By covariance operator. Maybe you understand that in finite dimensional case S is truly covariance operator of a random vector. So again, we have the funny situation when the Gaussian random element does not exist, but still it has a covariance operator S. Naturally, arise the question: can we have the Gaussian strong random functional for any good operator S? What does it mean, good? Let me recall you. Let me recall you definition of S. So S was defined as follows: S x y is equal to the expectation A of x, A of y. Yeah. And from this definition, one can derive good properties of operator S, namely, the first one. We already mentioned S is bounded, linear operator. The second one, S is self-adjoint. Really, here we can change multipliers easily, so we can change here x and y easily. Due to this, one can conclude that S is self-adjoint. Moreover, the last property is very important. S is greater or equal than 0. S is non-negative operator. S is non-negative operator. It means that since it is self-adjoint, it means that for all x which belong to H, we have S xx is greater or equal than 0. In general case, we have to substitute in S the a linear combination, but we already have that S is self-adjoint, so now everything is okay with such definition. It occurs that these three properties are enough for S to be a covariance operator of some strong Gaussian functional. And tomorrow or the next lecture, we will see why it is so. For today, that's all. Thank you for your attention. Maybe somebody have questions or comments, please. Okay, if there are no any questions, then we will continue our lecture tomorrow. And thank you for your attention.
Thank you, Professor.
Bye. See you tomorrow.
Okay, see you. Bye.